Right now, an object from another star system, 3I/Atlas, is tearing through our solar system, doubling in brightness every few weeks and building a green cloud 500,000 kilometers across as it barrels toward Mars. Astronomers expected a flicker. Instead, 3I/Atlas now glows 6 times brighter than predictions, confounding telescopes on Earth and sparking urgent debate over what's really fueling this outburst. A nucleus gone hyperactive, sunlight unlocking alien ices, or something stranger entirely. With its closest approach to Mars weeks away, and Earth's view about to vanish into the sun's glare, the race is on to uncover the truth. Before 3I/Atlas slips beyond our reach, what's driving this unprecedented display, and what secrets lie inside that luminous coma? At this moment, 3I/Atlas is about 2 astronomical units from the Sun. That's twice the distance between Earth and our star, or roughly 300 million kilometers out. Its velocity is staggering, currently traveling at nearly 60 kilometers per second and still accelerating. By the time it swings closest to the Sun at the end of October, that speed will peak near 68 kilometers per second. For comparison, that's more than twice as fast as any planet in the solar system, and enough to cross from Earth to the Moon in just over an hour. On the brightness scale, 3I/Atlas has now reached magnitude 12. That number might not mean much at first glance, but in practical terms, it puts the comet well out of reach for the naked eye. Even seasoned backyard observers need at least a medium-sized telescope to spot it, and only under dark skies. In fact, the difference between magnitude 6, the threshold for unaided human vision, and magnitude 12 is about 250 times fainter. And yet, despite these challenges, its apparent brightness has been climbing much faster than any model predicted. The coma, the cloud of gas and dust enveloping the nucleus, has grown explosively. Recent measurements suggest it now spans several 100,000 kilometers, rivaling the diameter of Jupiter. That expansion is not just a visual spectacle, it's also a key reason why telescopes are picking up more light from the comet than expected. As the coma grows, more sunlight is reflected and scattered, boosting the object's measured brightness even if the solid core itself stays hidden. Every major survey and observatory is tracking these numbers. The Atlas team, who first spotted the object in early July, logs each new position and brightness update in real time, feeding trajectory models and alerting the minor planet center of any sudden changes. With the Mars flyby and perihelion both on the horizon, these hard metrics, distance, speed, brightness, set the baseline for everything that comes next. In September, 3I/Atlas defied expectations with a surge in brightness. The light curve, which astronomers use to track how an object brightens or fades over time, veered sharply away from the predicted path. This wasn't a subtle uptick. It was a jolt that set off a flurry of debate across professional and amateur astronomy circles. At the heart of the puzzle is the comet's coma, the vast expanding cloud of gas and dust surrounding its hidden nucleus. As the coma grows, it reflects and scatters more sunlight, making the entire object appear brighter in telescopes. By early October, the window for observing 3I/Atlas from Earth is closing fast. Each evening, the comet dips lower into the twilight, pressed ever closer to the sun's glare. The angle between 3I/Atlas and the sun, astronomers call this solar elongation, shrinks below 30 degrees by October 21st. That's the threshold where even the largest ground-based telescopes struggle to separate the comet's faint light from the overwhelming brightness of the sky. For most of the world, the practical viewing window has already narrowed to a sliver of time just after sunset, with the comet barely clearing the horizon before vanishing into the haze. Amateur networks are scrambling to capture the last usable images. Online forums fill with reports of failed attempts and rare successes as observers race against the encroaching twilight. Some teams coordinate global campaigns, handing off observation duties from one longitude to the next in a relay, hoping for just a few more frames before the conjunction blackout. Professional observatories, bound by stricter safety limits for their sensitive optics, have already started to pull back. The risk of damaging equipment by pointing too close to the sun is real, and few are willing to take that chance. The urgency is not just about lost photographs. Once 3I/Atlas passes behind the sun from Earth's perspective, there will be a complete data blackout, No direct measurements, no spectra, no way to track changes in brightness or structure. For astronomers, that means every remaining observation before October 21st is critical. The geometry of the solar system itself is shutting the door, and the comet will slip out of reach just as it approaches its most active phase. The only hope for continued monitoring will come from assets far from Earth's line of sight, a problem that now lands squarely on the shoulders of spacecraft orbiting Mars. Mars, for a brief window, becomes the only outpost with a front-row seat to 3I/Atlas. As Earth-based telescopes go dark in the sun's glare, the focus shifts to a fleet of orbiters circling the red planet. Each mission brings a different set of eyes. The European Space Agency's Mars Express, with its high-resolution stereo camera and OMEGA spectrometer, can capture both images and chemical fingerprints from millions of kilometers away. The ExoMars Trace Gas Orbiter, equipped with NOMAD and ACS spectrometers, is designed to sniff out faint signatures of gases, water, carbon dioxide, even exotic volatiles, across the comet's coma. NASA's MAVEN, built to study Mars's upper atmosphere, can tune its ultraviolet spectrograph to catch emissions from the comet's gas and dust, while its plasma instruments monitor how the solar wind interacts with this interstellar visitor. Mars Reconnaissance Orbiter, famous for its sharp high-rise camera, has the potential to resolve the nucleus if conditions allow, though tracking a fast-moving comet is a challenge for any spacecraft. The geometry favors Mars. On October 3rd, 3I/Atlas sweeps within about 28 million kilometers of the planet, close enough for these orbiters to attempt direct observations, yet far enough to avoid dust hazard protocols that once hampered comet flybys. Instrument teams have spent weeks running simulations, updating ephemeris files, and negotiating precious observation slots. Every team wants a piece of the encounter: visible and infrared images to map the coma, ultraviolet spectra to measure gas production, plasma data to probe the comet's interaction with the solar wind. The hope is to catch the nucleus as a distinct point, separate from the sprawling coma, and to chart the chemical makeup of material released as the comet heats up. No mission has promised uninterrupted coverage. Observation plans depend on spacecraft pointing constraints, data bandwidth, and the unpredictable timing of the comet's closest approach. But even a handful of successful passes could deliver insights impossible from Earth: direct measurements of dust, gas, and plasma at a scale never attempted for an interstellar object. For now, the spotlight is on Mars, and the science teams are ready to seize this rare opportunity before 3I/Atlas speeds on toward its date with the Sun. The first thing anyone notices about 3I/Atlas is its striking green glow. Spectral analysts quickly zeroed in on this color, scouring the comet's light for chemical fingerprints. The consensus, backed by ultraviolet excited spectra from both professional and amateur teams, points to diatomic carbon, C2, as the main culprit. When sunlight hits carbon-rich molecules in the coma, it kicks them into an excited state. As these molecules relax, they emit a vivid green light, especially in the swan bands around 510 nanometers. This is a classic signature for active comets, but 3I/Atlas stands out for the sheer intensity of its green hue, even from a distance of 2 astronomical units. Not everyone agrees on the details. Some teams have flagged possible contributions from ionized carbon monoxide, CO+, or the cyanogen radical, CN, especially in the earliest September spectra. Both of these can also glow green or blue under solar ultraviolet, and debates have broken out in peer review threads over calibration scripts and the handling of background subtraction. Still, the most robust datasets, those with the cleanest, widest spectral coverage, consistently show that C2 emission dominates the visible coma. The chemistry here is more than just a visual effect. The rapid speed of 3I/Atlas means that solar radiation is slamming into fresh ices and dust at an accelerated rate, peeling off volatile molecules and mixing them into the coma. As a result, the green color isn't just a marker for carbon, it's a real-time indicator of how quickly the comet's surface is changing as it races toward the Sun. A growing number of observers have started to notice something odd about 3I/Atlas's appearance: a faint sunward feature stretching back toward the Sun itself. This so-called anti-tail runs counter to what most people expect from a comet, where dust is usually swept away from the sun by radiation pressure, forming a classic tail that points outward. In the case of 3I/Atlas, the geometry and the physics are conspiring to flip the script. When a comet races through the inner solar system at extreme speeds, as 3I/Atlas is now, dust grains ejected from the nucleus can actually move ahead of the comet's path, especially if they're large or electrically charged. From Earth's perspective, these particles can project a slender sunward spike, an anti-tail, visible only when the viewing angle lines up just right. Plasma physicists point out that the rapid expansion of the coma, combined with the comet's high velocity, creates a complex environment where electromagnetic forces rival gravity. Charged dust grains caught between the solar wind and the comet's own outflow can be focused into narrow streams. These sunward features aren't permanent. They depend on the interplay of grain size, charge, and the ever-changing direction of sunlight. The effect is amplified by the unique viewing geometry in late September, with 3I/Atlas's orbit, placing Earth almost in the plane of its dust sheet. So far, reports of a sunward anti-tail on 3I/Atlas remain tentative. Amateurs and some professional teams have flagged possible hints, but no peer-reviewed images or precise measurements have been published. The phenomenon itself isn't new to comet science, but its appearance on an interstellar object at these speeds is rare. For now, the anti-tail adds another layer of intrigue to an already unpredictable visitor, hinting at the complex dust plasma physics at play as 3I/Atlas barrels toward the sun. Every comet that visits our solar system brings its own quirks, but 3I/Atlas stands out even among rare company. The first two interstellar visitors, Oumuamua and 2I/Borisov, set the bookends for what astronomers expected. Oumuamua, discovered in 2017, was a dry, cigar-shaped object. No visible coma, no tail, just a tumbling shard that slipped through the inner solar system almost unnoticed. 2 years later, 2I/Borisov arrived with all the hallmarks of a classic comet. A bright, blue-tinged coma, a textbook dust tail, and a chemical signature dominated by water and cyanide, much like the icy wanderers that orbit the sun every few centuries. 3I/Atlas, though, refuses to fit neatly into either category. Its coma is not just large, but unusually green, a result of strong diatomic carbon emission not seen at this intensity in most solar system comets. The brightness surge, nearly six-fold above prediction, has no parallel in either Oumuamua's muted passage or Borisov's steady rise. And while Borisov's tail streamed away from the sun as expected, 3I/Atlas hints at a sunward anti-tail, a feature more familiar from the rarest solar system comets, but nearly unheard of in objects from interstellar space. Even among recent newcomers like C/2025 R2, Swan, and A6 Lemon, which displayed their own bursts of activity, 3I/Atlas is in a class by itself. Its speed, chemistry, and unpredictable behavior force astronomers to rethink the boundaries between homegrown comets and those forged in distant planetary systems. For classification teams, the challenge is more than just assigning a label. Each anomaly in 3I/Atlas's playbook is a window into physical processes that may have shaped small bodies across the galaxy. The stakes are high. Every new measurement has the potential to upend decades of assumptions about what it means to be a comet and what stories these visitors can tell about the worlds they left behind. After perihelion, 3I/Atlas will begin to fade, likely much faster than it brightened. Most models predict a sharp drop in apparent magnitude as the comet speeds away from the sun, its coma shrinking and dispersing into the dark. For anyone hoping to catch a glimpse, the requirements only get steeper. A telescope with at least a 20-centimeter mirror becomes the minimum, and even then, only the most sensitive digital cameras will pick up more than a faint smudge. Visual observers will be outpaced by the comet's rapid retreat, while image stacking and careful background subtraction will be essential for tracking any lingering activity. The practical side of comet watching now shifts to online dashboards and coordinated campaigns. Citizen science networks, some built around Discord servers, others hosted by established organizations, provide near real-time updates on the comet's position, brightness, and morphology. These platforms collect raw data from backyard telescopes across the globe, process it through shared pipelines, and post light curves that anyone can follow. For many, it's the first time a truly interstellar object's fate is being chronicled by amateurs in almost real time. The stakes for science don't end with the fade. Every new data point, each light curve, each spectrum, each disputed detection, feeds into a bigger puzzle. How do interstellar comets behave as they pass through a solar system so different from their birthplace? What can their chemistry, their dust, and their fading light teach us about the building blocks that shaped planets across the galaxy? The questions now reach beyond the observing field, inviting anyone with a telescope, a laptop, or even just curiosity to join the search for answers as 3I/Atlas slips back into the dark. With Earth-based views vanishing after October 21st due to superior conjunction, the October 3rd Mars flyby becomes the last opportunity for close-range, multi-instrument observations. No detailed mission schedules for Mars orbiters have been released, leaving gaps in our knowledge about upcoming data. Compared to Oumuamua and 2I/Borisov, 3I/Atlas displays a mix of comet-like and atypical features. What happens as it rounds the Sun, its composition, fade rate, and structural behavior will inform future studies of interstellar visitors. For now, the true nature of 3I/Atlas remains an open scientific question, grounded in hard-won evidence and awaiting its next close encounter.